This video demonstrates the use of SSTDR, spread spectrum time domain reflectometry, for the detection and localization of open faults in PV arrays. We test our method on two different strings of panels, each producing close to 1000 volts. We first test our method on 26 modules in series from Canadian Solar. Here is our laptop connected to the SSTDR device. The device is hooked up to our PV string with a 50-foot long pair of PV cables. There are two windows on the laptop. One, now shown in the bottom right corner, is a waveform of raw data collected by our device. Peaks represent reflections due to impedance discontinuities. In the bottom left is an illustration of the PV string. Faults as they are detected will be displayed here. Here, I take a baseline waveform which will be compared to future measurements and detect faults. We first introduce a disconnect at the negative lead of the PV cable. A peak appears in the bottom right, indicating that there is an open circuit. A fault is detected and shown in the bottom left. We then disconnect the other lead to show that our device collects data from both directions. Now technicians introduce disconnects between every pair of consecutive panels. When this first disconnect is made, a peak appears in the bottom right waveform and a fault is detected and located in between the first two panels. Another disconnect is made in between the next two panels and it is detected and located in the same way. As technicians move further down the loop, peaks decrease in amplitude and move farther to the right. You may notice that the location of peaks in the waveform are different from the location of faults reported on the interface. This is because the panels themselves contribute a significant amount of length that our signal has to travel through, but we compensate for this when reporting the fault location so that technicians repairing faults reported by our system don't have to worry about the electrical length of panels and can instead just walk down the length of cable that's reported. Eventually, this peak will decrease in amplitude enough to become indistinguishable from noise. Past this point, we cannot currently locate faults. With our current method, we're able to see through about 7 panels, and since our device measures in both directions through the loop, we can actually monitor 14 of the panels in this string. Next, we test on a string of 24 panels in series from LG. We induce and measure faults in the negative and positive leads. Both are located well, just as before. We then move down the string and induce disconnects between the panels. Location is good for the first couple disconnects, but these LG panels have multi-wire bus bars, which we believe create complicated reflections and might confuse our SSTDR device. As such, as we move down to the third, fourth, and fifth disconnects, our localization begins to jump around. We believe that future work in fault detection algorithms and the modeling of interactions between SSTDR signals and PV modules will allow for this to improve. Nonetheless, we are still able to detect and roughly locate open faults in between roughly 7 panels. It is worth noting again that our device measures from both directions, and we demonstrate this by having the technicians move down the other side of the loop and get closer to the SSTDR device. Faults appear closer and closer to the SSTDR as technicians move up the loop. The accuracy is still spotty up until the first 2 panels are reached. In the future, with simulation of SSTDR interactions, modeling of the environment, and the improvement of fault detection algorithms, our group hopes to improve the precision and range of this method. We would like to thank Chris Deline, Byron McDonald, and Josh Parker at NREL for help making this field testing possible. We would also like to thank the U.S. Department of Energy for helping fund this research. The specifications of all the PV modules used in this experiment are linked in the description, alongside links to prior work from our group. Finally, thank you for having interest in our research, and sincerely, thank you for watching.